Today I wanted to continue talking about kinetics, electrokinetics. Okay, and we established last time, we wrote that if we had an electrode, this is in your notes, at x equals 0, and we have C0 x of t, we could write the reaction velocity, which we said was a flux, as kf times C0, 0t. And this reaction is O plus n electrons going to R. And we said this is the cathodic current over NFA. And we said that the backwards reaction was KB CR 0T equals IA over NFA, the anodic current. And this is the flux. And what's the units on the rate constant? Did we do that last time? I don't think so. What's the units of Kf? Can anybody tell me? Well, the rate constant. So we know this has units of what? This has units of moles per centimeter squared, right? So this is a flux, right? And so we got that from this. And what's the units of the rate constant? So what's the, well, it can't be per second. Let's look at this carefully. So what's the concentration, units of concentration? Okay, often moles per liter. Let's do it in moles per centimeter cubed, just to make our life a little easier. I mean, it's a easy conversion between the two, right? So if I do that in moles per centimeter cubed, what's the units of the rate constant? Centimeters per second. And so this sort of odd-looking rate constant is very typical for heterogeneous electron transfer rate constants. So this is a heterogeneous electron transfer rate constant. So B net equals B forward minus B backwards is just the difference of these two things. I'm not going to write it out, but it's the total current over NFA, right? So total current is just current going that way minus the current going the other way, right? So where I equals IC minus IA. Okay, so that's the net reaction. So now we're going to use this introduction as the basis to derive the Butler-Volmer equation. BV, or Butler-Volmer. Okay, so Kf and Kb, these are rate constants, right? Are they going to depend on potential? So the way I framed the question, you would think the answer would be no, but they in fact do depend on potential. So they're rate constants, but they're potential-dependent rate constants, just like a rate constant depends on temperature, right? Same thing. So what we'll see here is the electrode potential will control the free energy of the electron, and will control how much driving force there is for this reaction to occur. So it's going to control it in that way. So what we need to do is we need to have a formalism to think about this. And so let's imagine a scenario. So let's just do something really simple first, and then we'll do it more rigorously. If I plot the standard free energy of the system as a function of the reaction coordinate, and imagine I have a sodium mercury amalgam. Imagine it's in contact with, say, electrolyte. What might happen to that sodium? It could give its electron somewhere, right? It could do a redox reaction with the electrolyte. So we can also draw a product, which is Na plus in solution, So the Na plus could transfer to solution, and maybe the electron in mercury, right? So this could we could have this system, right? We could leave the electron in mercury, and we could put the sodium plus in solution. So this would be the case of say you had a pool of mercury, and you're using it as an electrode, and you have it in contact with sodium plus in solution, right? And if I apply a very reducing potential, in principle, I can reduce sodium and put the sodium into the amalgam, right? And so what we can do is we can plot curves, and again, we don't know what this reaction looks like, but we can basically say, well, as we proceed through this reaction, the sodium has to sort of pass across the boundary between the mercury and the electrolyte, or also you can think about the sodium plus and the electron having to sort of, the sodium plus having to sort of push its way into the mercury so the electron can hop on it, right? And that's going to raise the energy of the system as you're sort of pushing it out of its local equilibrium. But then all of a sudden the electron is going to hop onto the sodium, and now you're going to have this sodium that's like sitting there, not fully coordinated with mercury. It's very high energy, but it can quickly go back into the bulk of the sodium. So that's kind of thinking about like a reaction path. And notice these are basically at the same level here. And I just drew them that way, right? And I drew them like that because this is equilibrium. This would be equilibrium, right? And this would be the case when your electrode potential was applied such that you're controlling, remember this is controlled, mu bar electron in mercury is controlled by potentiostat. So you control this, control the free energy of this basically, so you can move this level up and down. This level is just governed by whatever the free energy of that chemical compound is, right? But if I apply potential, so if I apply a reducing potential, right, I can put this, right, I can put that level up. So which way is the reaction going to go now? The net reaction. From right to left or left to right? It's going to go, you're going to take sodium plus, and you're going to make it into sodium right, because it's going to go downhill in energy. And notice that there's a very little barrier for that now that I've raised this up. Before there was a larger barrier, and I've raised it up, the barrier's gotten smaller, and the net rate's going to go that way. There'll still be a little bit going this way, but the amount going this way, going up this big barrier, is going to be much smaller than the amount going this way, right? Now, imagine if I apply a positive potential, an oxidizing potential, relative to the equilibrium potential. Remember, oxidizing and reducing, positive and negative in electrochemistry, they are relative terms to some reference, okay? And in this case, we've referenced to equilibrium. When these two things are in equilibrium, have the same free energy. So now what happens? Which way does the reaction go? Goes left to right, right? And if you see here, now there's almost no energy barrier going up here. It's like falling off a cliff, right? So it's going to be very fast. But going this way is going to be slow because there's an energy barrier. So the net reaction is going to go that way. So this is basically Butler-Volmer. So imagine now we're going to do this exact same picture, but in a little bit more rigorous way. So this is going to be on the y-axis. I'm going to again plot standard free energy. And we're going to do things, we're going to write things at standard state because that's going to be our reference state. And everything we're going to do is going to apply also to non-standard state. We're just going to do it at standard state because that's a reference. Okay, standard state's right 1 molar of species, all those sorts of things. Okay, so that's our reference. And we're going to imagine we have a reaction. And we're first going to imagine it at equilibrium. At equilibrium at E naught. Okay, so I'm going to draw this. At equilibrium at E naught. Okay? So let's do that. So I'm going to draw a curve here. And this is going to be O plus an electron. So I'm flipping around from here, but that's okay. Don't worry about it. O plus an electron. So the system is O in solution. the oxidized species in solution, plus an electron sitting in my electrode. Right, that's my system here, and this is the free energy of that system. Okay? And I can perturb it, like if I push O right next to the electrode surface, if I start transferring the electron over the interface, right? If I start moving the electron, the system's gonna have some different energy. There's all these degrees of freedom. If I vibrate the bonds of O, like if I say O is a transition metal complex, if I start pulling the bonds apart, that will raise the energy, right? So those are all different degrees of freedom of the system. And this is just, of course, the reaction coordinate, which represents sort of the lowest energy path over all those degrees of freedom. Okay, and then I can have a product, R. Now, if I'm at equilibrium at E naught, so this is at potential E naught, where should the bottom of this parabola be, or the bottom of this curve? It should be at the same level, right? So I should, basically do that, right? And then I can define some things like delta G double dagger. Let's see here. I can find this parameter here is delta G double dagger not for the cathodic process. Okay, so I'm under standard conditions at E naught. Standard conditions at E naught. This is the activation free energy for the forward cathodic process, right? And then I can do the same thing over here and write delta G naught double dagger for the anodic process. And they're the same, right? Under these reference conditions. What happens if I apply a potential now? So I want you guys to walk me through this. Say I apply a potential, oxidizing potential, E minus E naught. So the applied potential is not equal to E naught, right? So I apply some potential E, and that's not equal to E naught. That's a better way to say that. So apply some potential that's not equal to E naught. This is for E equals E naught, and I apply an oxidizing potential that's not equal to E naught. What's going to happen to this curve? Okay, I'll lower the energy of the electron in the electrode. So this curve represents the energy of what? Plus the free energy of O. Okay, but we're not changing the free energy of O, right? So we're just going to lower it. So, and how much are we going to lower it by? But what's the relationship between E and free energy? Negative N of E, right? And we're going to assume this is O plus 1 electron going to R. So this is a theory for 1 electron transfer. So we're going to lower it. And the amount we're going to lower it is just this distance here is just F E minus E naught. Okay? Right? Because that's G. Because N equals 1, right? So this is the difference in potential between here and here. You multiply by F to get free energy. So that's just F E minus E naught. And we're going to assume that it's going to equally shift the curve down for this whole surface. So the free energy surface is going to look like that. Okay? So I'm shifting it down by the same amount everywhere. And what you're assuming there is basically that this surface, the change in this surface is really due to modulating properties of O, like stretching the bonds, for example. And E is what is changing the horizontal position. Right? And in fact, there's an important point here, which I didn't mention. We'll get into more when we get to Marcus theory. When we think about this reaction progress, what the system is doing, well, what's first of all, what's the reaction going to look like here? Which way is the reaction going to go? Is it going to go forward or backwards? Backwards, right? Because the products have higher energy than the reactants. And the way to think about this conceptually is you have R, right? And in order for R to give its electron to the electrode, it needs to sort of adopt R needs to have the geometry of O. Because when you transfer an electron, it's via quantum mechanical tunneling. And quantum mechanical tunneling happens at the same energy. It's an iso-energetic process. You can't dissipate energy via tunneling. So it goes from one quantum mechanical state to another that are at the same energy. You can't launch vibrational modes. You can't dissipate energy. It's a quantum mechanical coupling process, okay? And so what has to happen for the electron to transfer is actually R and O plus the electron have to have the same energy. Because the system, what's happening here is the system is sort of being perturbed just by thermal vibrations, okay? The system's kind of exploring everywhere. And then at some point it has the right energy so that all of a sudden it can transition to being in this state. R and O plus electron are the same energy at this point, and then they can relax back down to the O plus E. So if you think about what the system is doing, is it's simultaneously exploring everything. It's going all over the place. Every so often it happens to find this point, and then half the time it'll go here, and half the time it'll go back to where it started from, roughly. But the thing is that randomly it'll find this point more often coming from this side than it will coming from this side, because you need less thermal energy to get up to that barrier. You see that? So we'll talk about this in more detail when we do Marcus theory, but this is the fundamental picture of electrokinetics. Okay, so what happened to the barriers? So now let's look at what happened to the barriers. So did this barrier here, we'll call this delta G double dagger A. It's not the standard state barrier, it's now the barrier under some applied bias. They get smaller or bigger? Smaller. That makes sense because its direction is going this way, right? And then let's look at this one. Did it get smaller or bigger? Well, it looks like it stayed pretty much the same, but that's the artifact of how I drew it. So I basically, didn't make these perfectly parallel. I mean, if you think about it, you're moving this down by this amount. So you're moving this down here by this amount. So you see how I actually didn't draw this right? I didn't move this. Anyways, so if I move this down by this amount, but this barrier only got smaller by a fraction of that because it's coming in at an angle. So let's zoom in on that and figure that out. How this works. Okay, so I'm going to zoom in now on sort of this area where they cross, okay? So we're going to zoom in. And, okay, standard free energy. And one assumption that Butler-Volmer makes, which, is it's an assumption. In reality, these are curved a little bit. These lines are curved a little bit. And in Marcus theory, we're actually going to assume they're parabolas. It goes x squared, right? It's distance squared, like a harmonic oscillator, quantum mechanics. Masses on a spring. In Butler-Volmer, we're going to assume that they cross as straight lines. It's like simplest possible model. And we're going to cross them like this. Okay, so we're zooming into that area. And then this is, of course, this is G naught again. And this is reaction coordinate. Okay. And on this side, we have R, O plus an electron. And then in pink, we had this other line here, which had the same slope. But was shifted. And how much was shifted by? Okay, this is F E minus E naught. Okay. So that's how much this curve has gone down, right? And what we want to know, so this is how much further down you have to come from, right? So if I had to get to the same point here, like imagine I had to get to the same point, then this is how much free energy, extra free energy I need to get there. But I don't need to climb over the same hill, right? The hill's got a little shallower. The elevation's got a little lower. I'm starting from lower. I'm starting from F E minus E naught lower, but I don't have to get quite as high. And this distance is important, we know that. So let's just get the color. Okay, so I'm going to put these 3 lines here. And this fraction, we're going to call this fraction here 1 minus alpha E minus E naught times F. And we're going to call this fraction alpha E minus E naught F. And as you can see, what's this fraction plus this fraction? What's it equal to? 1 minus alpha plus alpha. 1, so it's 1 times this term, so it's this, right? As required by the geometry, right? Okay, so we're just splitting up this total distance. So this curve went down by F E minus E naught. But a fraction of that doesn't count because this crossing point also lowered. So this is the net increase in forward barrier, right? Because if the crossing point decreased the same amount as this went down, it would cross over here. But it's not crossing there, it's crossing here, so the forward barrier has gotten bigger, right? So that's the net increase in the forward barrier. And then similarly, this one, the crossing point used to be there, but now it's here. This is the net decrease in the reverse barrier. So you can see what we've done, right? We've used a very simple model. Now we can write the activation barrier as a function of potential. Just like in the past, you could write, the rate constant as a function of temperature. Now we can also write as a function of potential, because potential is actually changing the size of the hill you got to get over. Yes?
I think I'm just confused. So that space is representing the increase in free energy of the forward barrier, but it looks to me like the forward barrier is lower than like...
Yes, but remember, good, this is a really good point. Remember our overall picture, this starting point dropped a lot.
Okay.
So like, I'm asking you to climb up Spencer's Butte, right? And instead of starting at the parking lot next to Spencer's Butte, you got to start in downtown Eugene.
Okay.
And then I say, well, you don't have to climb all the way over Spencer's Butte. Maybe if you just kind of get halfway up, it's okay. But it's still harder to start from downtown Eugene, right? What I would say is the crossing point only went down by this. The crossing point went down by this thing, which is smaller than the reactant energy went down. So the reactant energy went down this much, the crossing point went down a smaller amount, so the net is that it's harder to get over the reaction barrier. Okay, so if potential is changed by delta E, then negative F delta E equals negative F E minus E naught. Okay, so that's the change in the electrode potential and the change of the free energy. The reactant curve goes down. So reactant curve moves to lower G. The crossing of curves moves down a fraction of that. That's what we said over there, of negative F delta E. So I could write delta G double dagger anodic is equal to delta G double dagger not anodic minus this term that is lowering the barrier, right? F E minus E naught. So remember, going anodic is taking R and going to O plus an electron. And that's the barrier. When I move this down, that barrier got smaller, right? So that's lowering this barrier is smaller than this barrier, right? If you apply a positive potential. So alpha is going to go from 0 to 1. So this is going to be a positive number when this E is more positive than E naught, right? If E is more negative than E naught, this is going to be a negative number, and this barrier will go up. So we'll look at all those examples, but it's just, you can work it all out from just the simple crossing linear curves. So the cathodic barrier, so the forward reaction now, is equal to delta G naught cathodic plus alpha F E minus E naught. If E is more positive than E naught, more oxidizing than E naught, it becomes harder to drive a reduction process. Makes sense, right? And then we can write the rate constants, Kf, equal the attempt frequency times the exponent of delta G double dagger cathodic over RT, right? And K backwards equals the reverse attempt frequency, exponent delta G anodic double dagger over RT. Okay, so this is just the Arrhenius type equation, right, for the rate constant. And we can just take these terms here, right, and we can plug them in. I'm not going to do it because I don't want to take up the board space, but you can easily see that now the rate constant depends on the electrode potential, right? Because the barrier depends on the electrode potential, and the rate constant depends on the barrier. So let's consider a special case, a reference case. Let's consider this special reference case that we kind of started with, and we're going to use that to derive some standard parameters that we can use to compare kinetics of different reactions, okay? So let's imagine CO star equals CR star. What does the star mean? It's the bulk concentration, okay? So basically the concentration of O is equal to the concentration of R. So what is E for the solution? E is equal to? E naught. E naught. Actually the formal potential technically because the activities can be different, but E naught, okay? So we're at standard conditions basically. So E equals E naught. So at equilibrium, what do we know happens at equilibrium? What sort of, what do we know about this reaction at equilibrium?
Okay, I think maybe they're the same.
They could be. More precisely than Kf and Kb being the same. Remember, those are rate constants. What's the same?
Yeah, maybe.
The rates, exactly. The reaction velocities are the same. Now, if the concentrations are the same, you had a good foreshadow moment there. The rate constants will also be the same. So let's see that. So the reaction velocity is going to be Kf CO star, right? Because at equilibrium, the bulk concentration and the surface concentration will be the same. There's going to be no concentration gradients at equilibrium. And that has to equal the backward rate. But if CO and C star are the same, those cancel. And what we get, Kf equals Kb equals K naught. And we're going to call this the standard rate constant. And this, of course, only applies under these conditions. So this is a requisite for this to apply. But that's nice because then we can find a rate constant for any system. And we can tabulate those rate constants, those standard rate constants, and we know what conditions they apply to. And then we're going to use that standard rate constant to figure out the rate under any non-standard conditions. So it's just like tabulating standard values of free energy or something, right? And being able to then calculate it under non-standard conditions. So let's give a sort of a definition of K naught in words. So K naught is the standard rate constant, so we define that. Let's write it again. And it is the, what do I call it, the kinetic, it's related to the kinetic facility, so the kinetic ability or the speed of a given redox couple. So for example, if you're doing electrochemistry on ferrocyanide, which you did in lab, the kinetics are actually quite fast. If you're doing electrochemistry on water and oxygen, it's a 4-electron process, the kinetics are very slow. So they have very different K naughts by many, many orders of magnitude. Another way to say this is large K naught, equilibrium achieved fast, small K naught, equilibrium achieved slow, and maybe so slow that you never measure it in your. So one kind of analogy I like to use with the standard rate constant is imagine I have two big cylinders of water, okay? And they're connected by a small hose, right at the bottom, small hose. I let them sit there for a really long time, and if one starts out a little higher than the other, slowly the pressure will push the water through the hose and raise the level of the other one, right, until they're the same. So they're in equilibrium. Now imagine I come along with a 5-gallon bucket and I dump 5 gallons of water into one cylinder. How long will it take for the other cylinder to equilibrate? Probably depends on how big the hose is, right? So if it's a straw, it takes to take a long time. If it's a fire hose, it's going to happen very quickly. The size of the hose is K naught. Right? That's all it is, how fast the system can move between being in state A and state B, between products and reactants. So Kf, we can now write as AF, the exponent of negative delta G double dagger forward over RT, not cathodic, I picked up the forward from there, but that's the cathodic process at standard conditions. So this is what it would be in our equilibrium state. But remember, this delta G is changing, right? And so to account for that changing, we have this other exponent, negative alpha F, talk about F in a second, E minus E naught. And so this term here, if I multiply these two exponents together, that's just delta G naught C double dagger minus this term, right? Which is the exact expression we wrote for the forward barrier. So this is nothing different than I wrote before. I just split up the two exponents. Okay? And it turns out that this is K naught, right? So this is K naught. Why? Because when E goes to E naught, right? This term, what happens to this term? If E is equal to E naught? Goes to 1. And so this term doesn't depend on potential. This is K naught. This is the rate constant under standard conditions. Okay, and then F is just a shortcut. F, this curly F is just big F over RT. So that just helps us out a little bit, keeping the notation a little more compact. So Barton-Volker uses this curly F. And so I can write KB the same way, right? AB back, the exponent of negative delta G naught naughty double dagger over RT, exponent alpha F E minus E. Okay? Oh.
1 minus.
There should be 1 minus. I wrote the same term twice. Sorry. So there it is. Now we have the rate constants as a function of potential applied. So the total current, I equals IC minus IA, the anodic current minus the cathodic current, equals NFA, our conversion factor, to go between reaction velocity and current, right, times the rate of the forward reaction, Kf times CO 0T, minus the rate of the reverse reaction, Kd CR 0T, right? That's easy, so that's I. Everybody see that? That's what we wrote before. This is the rate of the forward reaction, the rate of the reverse reaction. This is multiplying them by our conversion factor between rate and current, right? Just the charge on a mole of species, the area of the electrode, the number of electrons transferred. I think in this case, we put N in, but we'll drop that in a second for a one electron process. And now we can expand these, right? We can expand these rate constant terms, recognizing that these are just K naught. Okay, so I'm going to plug these terms in to here, and I'm also going to recognize these are just K naught. Okay, so then I just have I equals, and I'm going to take N equals 1 actually, FA K naught, C0, C naught 0 T, EXP, negative alpha, F, E minus E naught, minus CR, 0 T, E, XP, 1 minus alpha, F, E minus E naught. Just another parentheses there, okay. Now you have an expression for current. So this is basically it. We'll talk about various ways to evaluate different components here, but there's two components. There's a forward current, the forward cathodic current, and there's a reverse anodic current.
Our exponent.
Well, this is basically just saying that, unless I wrote it wrong, let's see, make me think about the signs. So if E is more positive than E naught, right, then you should drive so if E is more positive than E naught, you should drive a net anodic current. So this needs to go to 0, right? So this rate should go to 0 as we make this very positive. So is that what happens? It does, right? Because E is very positive, this will be a big number. So it'll be 1 over a big number. So it doesn't matter how much O you have, it doesn't matter what this is going to go to 0. And that just came out of how we defined the barriers changing. But I agree it gets confusing. I've confused myself several times over the course of teaching this course and thinking about this stuff. And this one, the same thing. So what happens as E gets very large? In this one, 1 minus alpha, alpha is always going to be less than 1. So 1 minus alpha is always positive. E gets very large, E minus E naught gets large, the current goes up.
Infinity.
It goes to infinity. But it'll actually not go to infinity because this term will go to 0. Because you can't supply stuff to your electron surface that fast. And we'll see that in a second. So let's look a little bit more on alpha. Alpha is called the transfer coefficient in this model, this is simply a model of reality. It's not reality, right? It's just a simple model to try to figure out how nature does stuff, how nature transfers electrons. It's a really simple model. We're gonna define what alpha is rigorously, but practically it's a fitting parameter. So what people do is they fit their data to this, and they fit some alpha. Okay, that's practically what happens. They might try to interpret that in terms of this simple model. I actually think the simple model doesn't actually give much physical insight into the meaning of alpha. But I'm going to give you what physical insight there is. So we defined this crossing, remember? So this is our crossing. And we define some things here. So this is alpha FE here. This is 1 minus alpha FE here. I'm going to call this angle theta and this angle phi. And I'm trying to get some physical model. I'll use geometry basically to understand alpha. And so if I go through the trigonometry, I can see that alpha is actually equal to 1 over tan theta or tan phi over tangent of theta plus 1, or more simply, I should have just written this, tangent of theta over tangent of phi plus tangent of theta. Okay, so it's related to these angles, and these angles are related to how these things cross, right? You could imagine changing the relative size of these angles by changing how these curves cross. Like, what if I took this curve and made it like really sharp? So alpha is sort of conceptually in this model related to the crossing of the product free energy surface with the reactant free energy surface. So it's kind of the shape of the reaction barrier. That's the way people like to think about it. If you think about you're hiking up Mount Pisgah or something, you know, some parts are shallow, some slopes are steep. You hike up Mount Everest, it's going to be different, right? Alpha is related to that. So let's do some examples and talk about sort of how alpha can influence things. So what electrochemists usually do, because it's easy, is we just say, you know, alpha is probably about 1/2. And so what does that mean? If alpha is 1/2, what does that tell you about the angles from that equation?
Yeah, equal.
They are equal, right? Because if theta equals phi, this is going to be 1/2, obviously, because it's like x over 2x. So usually people just assume that, and that's basically a symmetric barrier. So theta equals phi, alpha goes to 1/2, and if I plot this, what that means, the crossing is symmetric, okay? So the barrier is symmetric. So one side, when you change the electropotential, one barrier gets larger by the exact same amount, the other barrier gets smaller. And you can see that from a symmetric crossing, right? Because if alpha equals 0.5, if you go back in your notes, alpha is the same as 1 minus alpha, which are the prefactors in those terms that modulate the rate. So if you remember these terms, then we had like the current equals NF, A, K naught, exponent, alpha, F, E minus E naught, right? And then we had another term that was 1 minus alpha. Alpha and 1 minus alpha are the same if alpha is equal to 0.5. So it's basically saying if alpha is 0.5, if I apply potential, the forward rate constant is going to decrease by the same amount on a log scale, the same amount that the reverse one is going to increase. Right? The barrier is going to change in the same way for both of them, but in opposite direction. So it's symmetric. Okay, but you don't have to have a symmetric crossing. Right? So we can have an asymmetric crossing. And we'll just consider two cases. So let's say alpha is smaller than 1/2. And so in this case, and you can see that from the angles, we're going to just erase the formula, but in this case, the R curve might be very steep, okay? But the O curve might be shallow. So now what happens? So I change this, right, by FE minus E naught. So I've changed where I start by a large amount. Did I change my barrier by a large amount or by a small amount? How much did the barrier height change? Okay, so did the forward barrier change much?
No.
Not much. Imagine this line was perfectly straight. It wouldn't matter where you put it, right? If this was a vertical line, it wouldn't matter where you started, you got to climb the same amount to get to the crossing point, right? Because this free energy surface has no curvature in it, okay? So that's one limit, right? That would be alpha equals 0. That would mean you apply potential and it only affects the reverse rate. Because the reverse rate, it changed by almost that entire amount, right? The barrier changed by almost the exact amount that I changed the electropotential. So that's alpha equals 0. You only change one process. And there are situations that are sort of akin to this. One of them is actually a semi-pure photoelectrode. Actually, it can be thought of to behave this way. So let's do one more. Now, once you guys write in your notes, predict alpha much greater than 0.5, or alpha greater than 0.5. So kind of draw what you predict for, say, alpha is going to almost 1. What would you predict? Okay, so to recap, for alpha is greater than 0.5, you have all the potential changing the forward reaction barrier and the reverse reaction barrier not changing at all. Okay. So let's think about the Butler-Volmer model a little bit more now, in the last 5 minutes. So at equilibrium, current equals what? 0. Forward current, the reverse current, that's the definition of equilibrium, right? So I equals 0. And electrode should adopt what potential? How would you figure out the electrode potential under these conditions? If you had some O and R and the current was 0 and everything was in equilibrium. Nernst equation, right? We could use the Nernst equation. So the electrode should adopt potential governed by Nernst. Well, right, CO star and CR star, right? Because the surface concentrations are going to be the same as the bulk concentrations under these conditions at equilibrium. So what I can say is, well, the forward current, IC, equals IA at equilibrium, right? And so I can write that. F A K naught C naught 0 T equals E negative alpha F E EQ minus E naught equals F A K naught CR 0 T E to the 1 minus alpha F E EQ minus E naught. So there's nothing fancy here. This is just the forward and reverse currents set the same, right? Nothing fancy. There's some things that cancel out here, right? What equation is this, by the way? If you had to guess. The Nernst equation. This is the Nernst equation. We better get the Nernst equation, right? Our kinetic model, if we go to equilibrium, better give us thermodynamics. Because if it doesn't, the kinetic model is wrong. So let's solve this. So I can write, and these, at equilibrium, these are going to go to CO star and CR star, right? Because there's no concentration gradients in equilibrium. So I can solve this, CO star over CR star. CO over CR is going to be equal to these two terms, e to the 1 minus alpha, EQ minus E naught, over e to the negative alpha f, I missed an f there, EQ minus E naught. I'm leaving that EQ here because, of course, it's the potential at equilibrium. We define that at current 0. And that, if I look at this, right, if I divide two exponents, it's like subtracting them, right? So this term here is going to cancel out the alpha term there. And so that very quickly gives me e to the f, EQ minus E naught. And this is the exponential form of what? The Nernst equation. And I can see that by just taking the natural log of both sides. Right, so I have ln CR star over CR star. Natural log of that side is big F over RT. EQ minus E naught. And I rearrange and I get E equilibrium equals E naught minus RT over F ln CO. CR actually, let's see here. Plus ln CO star over CR star. Okay, good. So our kinetic model at least converges to the thermodynamic definition based on free energies and reaction quotients that must govern the system in equilibrium.